Alright, before I begin, I do want to apologize if the audio doesn't align or is a bit choppy with some background noise because I'm recording it from an external device. It doesn't work on my iPad. I tried. I've been doing it for the past 30 minutes and basically have been recording an audioless video. Alright, let's move on. Okay, so for paper 5 reflection, I did 2 past year paper. One of them is this one, which is 9701. Paper 52 of the Feb-March 2023 series. So it is a fairly recent past year paper, a little over a year, slightly over a year ago. And yeah, we'll move on. Okay, so for this question, we are met with equilibrium and some calculations. This one is not the calculations, but it will come out after this. Okay, so right, let's read the question. Fe2+ are usually kept in acidic conditions to prevent them from being readily oxidized into Fe3+. Fe2+ reacts with Ag+ ions in a redox reaction. The following equilibrium is established. So we sort of get a glimpse and the idea that we're dealing with an equilibrium reaction here. So there are some steps you might expect, such as leaving it out or shaking it. Alright, the concentration of Fe2+ at equilibrium can be found by titration with a standard solution. So the standard solution they're referring to is likely to be a solution with a known concentration because, again, for titration, you can't perform an unknown concentration of solution with an unknown concentration of solution. That's not possible. You perform known with an unknown. Alright. Of aqueous potassium manganate 7 or KMnO4. KMnO4 is the purple in color. The equilibrium constant for the reaction can be found using the following equation. So the equation looks like it might be used later on. They'll probably ask about it. Okay, so yeah. We'll read the steps of instructions. A student carries out the experiment using the following instructions. So you add 100 centimeter cube of 0.2 mole. I'll just refer the concentration as just mole because it's easier for me to say that way, right? Okay, 0.2 mole of AgNO3 to 100 centimeter cubes of 0.2 mole of FeNO3 So looks like we're adding a 500 centimeter conical flask, which itself already contains FeNO3 2. We're adding AgNO3 to that. And okay, and you stopper the flask and label the conical flask A. You leave the conical flask A for 4 hours, shaking intermittently. Then leave conical flask A untouched for an hour. Right. So I've done a few diagrams which might help. Okay, so again, you are likely leaving it for 4 hours and shaking it intermittently for the purpose of it reaching the equilibrium, and you're shaking it so that the reaction can happen faster. So the forward happens faster, the backward also happens faster. So essentially it doesn't really affect in a way, but yeah. Then you leave it untouched for an hour, not shaking anymore. This is likely because it might produce some solid settle, and you want to settle the solid at the very bottom. Alright, okay. Use the pipette to transfer 25 centimeter cubes of the solution from conical flask A into a clean 250 centimeter cube conical flask. Label this conical flask B. Alright, so looks like we're transferring 25 centimeter cubes of whatever we have in A into B. It's still the same stuff, it's just less. Alright, okay, and then after that you're adding 5 centimeter cubes of 1 mole of NaCl to the solution in conical flask B. A white precipitate of silver chloride then forms. Alright, you add NaCl, then white precipitate forms. And step 5. Use a measuring cylinder to add 20 centimeter cubes of 1 mole sulfuric acid to conical flask B. Alright, so you're adding sulfuric acid. This is slightly in excess. That's why they're using measuring cylinder, because measuring cylinder tends to be very quick, very efficient, but not the most accurate. So yeah. Step 6. Rinse a burette most likely with KMnO4 itself. Yeah, and fill it with a standard solution of KMnO4. Step 7. Add KMnO4 to the mixture in conical flask B until the endpoint is reached. So you are probably expecting a pale pink color. Yeah, from colorless to pale pink. And yeah, step 8. Empty conical flask B and rinse it with distilled water, ready for the next titration. Okay, the student repeats the titration until concordant readings are achieved. So consistent, concordant. Right. The student records their result in table 1.1. So again, this one is very, very simple, right? Flashback to AS. We did this a lot, but we did it like experimentally instead of having the values, the data given. So yeah, all you have to do is subtract the final with the initial bread reading and you have the titer. Okay, so that is only 1 mark. Very unfortunate. Okay, for II, show clearly how you obtain the mean titer. Again, not new to this. To obtain the mean, you add them all together. You find the sum divided by the amount of titer. You have 4 different titer. So you add them all together, divided by 4, and you have 9.95. That would be your mean. Question B. See, they're now asking for what the standard solution is. It is a solution of a known concentration. Alright, okay. CI. Suggest why conical flask A is left for 4 hours. Again, it is to allow it to reach the equilibrium state and not shaken to let the solid settle. Alright. D. Again, they're also asking the same thing, for why is measuring cylinder the most appropriate. Again, acid is in excess, and again, measuring cylinder, it's not very accurate, but it's quick and it's efficient, so that's why it's the most appropriate one, because at the end of the day, it's already in excess. Doesn't matter about the accuracy. Alright, state what the burette should be rinsed with. Again, it's your KMnO4, alright, you should be expecting that. And for the color change, again, it's from colorless to your endpoint, pale pink. Okay, the student repeats the experiment using KMnO4 at a lower concentration. The student obtains a larger mean titer. Alright, suggest reason why a larger mean titer is better than a smaller one. Well, because the uncertainty is due to the actual instrument itself, right? It's due to the apparatus. So if your titer itself is higher, then it will decrease the percentage uncertainty. So again, less error, less percentage uncertainty. That is why it is better. Alright, for H, the equilibrium is shown. We have the equilibrium between Fe2 plus, Ag plus, which forms into Fe3 plus, and Ag. Alright. When another student carries out the titration with 0.2 mole of KMnO4, the mean titer is 21.1 centimeter cubed. So this is likely a different experiment. It is still titration, but a different one. Alright, okay. The ionic equation for the reaction between MnO4 minus ion with Fe2 plus is shown. Okay, so first thing first, they're asking for the concentration of Fe2 plus. Alright. Okay, this one is fairly simple. Usually they require you to find the mole of something, and then you find the molar ratio, and then you find the concentration. The same thing in this case. So we are given the concentration and the volume for your manganate ion, right? So you just times it, 21.1 times 10 to the power of negative 3. Make sure to convert it into decimeter cube and not leave it in centimeter cube. So yeah, you times it by the concentration and you have the value of the mole, which is 4.22 times 10 to the power of negative 4. And as you can see, the molar ratio is 5:1, so you times it by 5. That way you have the amount of mole for your Fe2 plus. But that is the amount for 25 centimeter cube solution. They're asking for the concentration in terms of decimeter cube. That's why you divide it again by the volume of solution. And that way you get 0.0844 mole per decimeter cube, and that is the concentration. Alright. Suggest why it is not necessary to measure the concentration of Ag plus ions in the equilibrium mixture experimentally. Alright, So if we take a look at like the equilibrium equation, right? The molar ratio for your Fe2 plus and Ag plus is actually the same. So what does this say? This indicates that the concentration is likely to be the same. So it is not necessary to measure the concentration because they are the same, concentration of Ag plus and concentration of Fe2 plus. So yeah, determine the decrease in concentration of Fe2 plus from the initial solution. Hence, determine the concentration of Fe3 plus in the equilibrium mixture. Alright, this one is fairly easy. It's just a simple subtraction. 0.1 minus your value in Hi, so 0.1 minus 0.0844, you get 0.0156, and that would be the concentration of Fe3 plus in the equilibrium mixture. Alright, determine the value of Kc. This is where you plug in the equation that was given initially, like in the first part of the question. I can't exactly go back because then I would have to undergo the animations again, but yeah, that was given, and you just plug in the concentration values because obviously from the previous questions you already found it. So 0.0156 divided by 0.0844 square, and yeah, you have the value 2.19. And for the units, again, the units for concentration is mole per decimeter cubic, and then mole per decimeter cubic over mole per decimeter cubic square, you get per mole decimeter cubic. Alright, okay. Now that sums up question 1. We have question 2. The reaction between iodide ions, I- and aqueous hydrogen peroxide, H2O2, takes place in acidic conditions. Reaction 1. 2I- iodide ion and your hydrogen peroxide forms your iodine. Okay, so again, it turns it from colorless to brown, but you added with a known amount of aqueous thiosulfate ions in the mixture. So, bye, lagi record. Alright, so you add the mixture, so you add your aqueous thiosulfate ions in the mixture, so it reacts with your I2 and it immediately turns it back to your iodide ions, so it is now back to colorless. So in this case, your limiting factor would be your aqueous thiosulfate ions. Alright. After all of the thiosulfate ions have been reacted in reaction to any further iodine form is detected using starch indicator. Okay, the following materials are used: 50 centimeter cubic of beaker containing the correct mass of solid potassium iodide crystals needed to make. They'll probably ask, how are you going to make that solution? Okay, 250 centimeter cubes of 0.1 mole decimeter cubes of Ki, 0.1 mole decimeter cube of Na2S2O3, same amount of concentration for H2O2, 0.2 mole per decimeter cube of H2SO4, your starch indicator, distilled water. A second student looked at the equation for the reaction 1 and stated that the order with respect to the concentration of iodide ions must be second order because the balance equation contains 2 iodide ions. This one just doesn't make sense straight up because, again, order can only be determined experimentally. So yeah, you have to perform experiment in order to determine the order. You can't just like take the balance equation and assume, oh, because the molar ratio here is 2, then it's second order. No, you can't. You can't just do that. Alright. Describe how the student makes 250 centimeter cubes of 0.1 mole per decimeter cubes of Ki, starting from the sample of solid potassium iodide in the 50 centimeter cube beaker. Give the name and size of any key apparatus used and describe how the student ensures the volume is exactly 250 centimeter cube. Alright. Okay, so first things first, this is fairly simple. It's a very easy question to score marks at. So like free 3 marks. Okay, so first thing you want to do is dissolve the solid using distilled water in the beaker. And second thing is to transfer the solution containing the beaker, including the washings, because usually when you transfer something, you don't transfer the whole thing entirely. Like some things are left out, for example, like some solution might get stuck in the walls of the beakers and so on, right? So you want to include the washings, and you rinse it multiple times into the 250 centimeter cubes of volumetric flask. Now I have shown a diagram of what you expect a volumetric flask to look like. As you can see, there's a marking at the very top, so you have to ensure that you fill the volumetric flask up to the mark. So yeah, you can top it off using distilled water. Alright, next part. The student carries out experiment 1 using the following steps. Add 25 centimeter cubes of 0.2 mole of H2SO4 into a conical flask. Add 20 centimeter cubes of distilled water into a conical flask from a burette. Add 5 centimeter cubes of your 0.1 mole of Ki. Alright, add 5 centimeter cubes of 0.1 mole of your Na2S2O3. This thing is what? It basically switches your iodine into your iodide. Alright, add 2 centimeter cubes of starch indicators to the conical flask. Use the burette to add 10 centimeter cubes of 0.1 mole of H2O2 to a small beaker. Add the contents of the beaker into the conical flask and start a timer immediately. So from the steps, I'm sensing they might ask why is the value different? And it's usually either you started the timer too late or too early. It's depending on your value. Alright, okay. Alright, so we have a table with 7 sets of data. Alright, state how the students could improve the reliability. This one is very straightforward. You can just repeat the experiment, find the average, find the mean, and ensure that the values are already consistent. Okay, so state the independent variable in experiments 1 to 7. So what exactly is an independent variable? Independent variable is the only variable that you change in a reaction, because it is to ensure that it has to be a fair test. There can only be one independent variable. So yeah. And there are also other terms such as controlled variable. Controlled variable is basically what you control, what you keep constant, what you keep as the same. And dependent variable is basically the effect of the independent variable. For example, if you give more water, the plant will grow taller. The grow taller part would be your dependent variable. Alright. In experiment 5, the starch indicator changed color immediately on adding H2O2. The student realized an error has been made. Suggest which step was missed in experiment 5. Okay, so the student probably forgot to add Na2S2O3 because that one is the one that is responsible from turning it into back into iodide, so it doesn't stay as iodine. But clearly it changed color, so it was still iodine and nothing has been changed. Alright, okay. The rate of the equation is represented as K to the I minus power n, and then I minus is proportional to the volume of Ki, and is the order of reaction with respect to I minus, and the rate is proportional to 1 over T. Alright, log rate equals to log K plus n log I minus. So this one is likely the line of equation. If they do ask what is the gradient, what is this, what is that, what is the y-intercept, you can use that equation probably. Next, use the result from the student's experiment in C to complete table 2.2. V is the volume of Ki and T is the time taken for the color to change. Give all values to 3 significant figures. The result for experiment 5 should not be used. Okay, so basically all you have to do for this step is just to plug in your values. Just plug in whatever is given in the table and you put log in front of it. Just ensure that you're not plugging in the wrong values because the entire thing is only 2 marks, and if you missed one, you're probably already losing a single mark. Alright, so again, make sure to give your values to 3 significant figures because they're asking you to do so, and make sure to round it correctly. If it's like 5 and above, you round it up. If it's like below 5, then you round it down. Alright, okay. Plot a graph on the grid to show the relationship between log v and log 1 over t. Use a cross X to plot each data point. Draw a line of best fit. Alright, okay, so as you can see, I tried plotting some points, but it's not complete. It's because I was using Keynote and it's impossible to draw the line of best fit. So yeah, I will fix this later on. And again, use the value you have obtained. So plug it in, the value of log v, this one would be x, will be your x, and your log 1 over t would be your y. Okay, and there you go, it's fixed. Okay, so again, that is the line of best fit. Make sure to draw it correctly because usually they'll ask for the gradient. And yeah, usually there is also an anomalous point, and they will ask, oh, what is the possible cause of anomalous point? What happened? Usually it's like incorrect timing, starting the timer too late or too early, stopping it too late or too early. It really depends on where the value lies. Alright, okay. See, this question, triple I, they're already asking for it. A timing error caused the most anomalous point on the graph. Circle this point and explain the error in timing which led to this point. Again, as we can see, the anomalous point is lower than it should be. So what does this mean? Your log 1 over t is lower than it should be, meaning your t is higher than it should be. So it means you either started the timer way too early or stopped the timer way too late. That would be the answer. See? Higher than it should be. Alright, okay. Use your graph to determine the gradient of the line of best fit. State the coordinates of both points you use in your calculation, and these must be selected from your line of best fit. So as you can see, one of them is already there. The other one is there. There you go. Alright, so again, we're no stranger to the formula for gradient, right? Change in y over change in x. And I basically use like the very top point and the very bottom point. So like negative 2.52 and like negative 1.64. So I covered basically the entire area, but you don't have to do that. As long as you cover at least 50% of the area, then it's already fine. Just make sure that it is at least 50% of the area. Okay, so yeah, change in y, change in x. Overall, the gradient value I got is 1.1. I'm rounding it off to 2 decimal place because they asked for it, so 1.10. Okay, the total percentage error from measurements is determined to be 5.25%. The true order of reaction is 1. Use this and your gradient from div to determine whether the error in experiment could be accounted for by the error from measurements or is it caused by other factors. Show any working. Okay, so for your percentage error, it is basically like the change in your gradient, so delta gradient over your true order of reaction. So again, 1.1 minus 1 over 1 times 100, there's a lot of ones, it's 10%. So again, 10% is larger than 5.25%. So yeah, the experimental error involves other factors outside of the apparatus, and yeah, other factors outside of the apparatus cause the error or the difference. Alright, that sums up this paper. It's a fairly short paper. Overall, it wasn't too bad except for the first part where you might get shocked especially with the equilibrium. Actually, like, the answer itself makes a lot of sense, but when we're like first exposed to it, it's like we're not used to like this style of asking like unexpected. Like, you don't expect someone to ask you like, oh, why did you leave something for 4 hours? Like, it does make sense, it's for equilibrium purpose, but sometimes when you're just first approaching the question, the thought didn't cross over your head. And overall, yeah, it's not too bad, and yeah, it's a fairly decent paper. Thank you for watching.